All right, I'd like to talk to you today about transforming functions and how modifying the parent function of a certain type can transform it and move it about the coordinate plane. So I'm going to get started with the absolute value function. You'll remember we took a look at this a little while ago in my class. F of x equals the absolute value of x is the parent function, and that one's plotted here. So if then I move over g of x equals the absolute value of x plus 5, I just kind of did some arbitrary modification to that. Then I plot that function. What I see is no matter what value of x I use, I have 5 additional units added to the y value, thus creating a vertical shift of 5 units in that graph. Well, if I modify this function a little bit and instead of adding 5, say I want to subtract 3, I, I believe what that will do is create a vertical shift down 3, test it, and indeed I'm right. So it seems then that adding or subtracting a value outside this absolute value sign does a vertical shift on the graph. Well, let's go ahead and test what happens if I move that add or subtracting inside the absolute value sign, such as here. The absolute value of x plus 3 as a quantity. So I'm going to plot this function and see what it does. Well, look at that. It moved left 3 units. So when x is negative 3, I get 0 for y. When x is 0, now I get 3 for y. Whereas before, when x was 0, I got 0, and when x was 3, I got 3. So adding 3 does a left shift by 3. What if I change that and I subtract 4? Doing the opposite thing, I think I should go the opposite direction, and I should go 4 units. So I'm predicting a right shift of 4. Yes, indeed, I did translate that graph to the right 4 units. So it seems then if I add or subtract something inside the absolute value, what I get is a shift in the opposite direction. When I subtract, then I shift right, and when I add, I shift left. All right, well, let's try another modification to the function. Let's try multiplying by a value. I predict that this is just going to kind of squeeze it together, so we plot that function, and yes, indeed, it has squeezed the absolute value function together. If I modify this a little bit and make it like 5, it should just squeeze a little bit more, and that's what it does. What if I made it negative 3? What will happen there? Well, now it reflects it. In addition to squeezing it together by that factor of 3, I've gotten a reflected value. So a negative 4 should do the same thing. It should just squeeze it a little bit more, but keep it down below that x-axis. And that's indeed what happened. Okay. I'm also going to modify this and say, what if I put in a decimal or a fraction of some sort? I'll just type it in as a decimal because that's going to be a little faster. But we'll think about 1/2 x, the absolute value of x. Now, instead of squeezing it, I've stretched it out a little bit, changing the angle again that it makes with the axes, but I've stretched it out. So if I change this to be 0.1x or 1/10 x, then indeed I've stretched it even more. Um, so I kind of can get a understanding of how that affects the graph. So if I get the function here that has 2 times the absolute value of x plus 3 minus 4, I'm putting all of those transformations together. What I'm predicting out of this is this 2 is going to squeeze my parent function together a little bit. This minus 3 is going to shift me left 3, or I'm sorry, the plus 3 is going to shift me left 3, and the minus 4 is going to shift me down 4. So I'm predicting a vertex at negative 3 comma negative 4 and a little more narrow than this graph here. So I'm going to go ahead and plot this function, and indeed that's what I've found. It is a little more narrow. You see it has a slope of 2 here, and then this would be technically a negative to slope, but based on it's got a ratio of 2 change in y for every change in x. And indeed, it has that vertex move to -3, -4 as I predicted. So if I change any one portion of this, then I'm just doing that same sort of modifications as I did before. So I change this to -7, then what I'm going to do is I'm going to shift right to +7 for its vertex. It'll still be at -4 here. And yep, it's just moved that graph over. All right. Well, let's see what happens with a linear function here. I have the parent function f of x equals x graphed, and now I've done a couple of modifications to just the simple linear function. I've scaled it by a value of 2, and I've subtracted 4. Well, I know that 2 is a slope, just changes its slope, so it's up, instead of over 1 up 1, it's over 1 up 2, over 1 up 2. And this -4 changes my y-intercept to -4. So the -4 acts just like the -3 outside of this absolute value did. It does a vertical shift of some sort. And the 2 acts just like the scale factor on the absolute value did. It creates some sort of change of angle with the axes. That's my prediction. So I plot that function, and indeed, it is change of slope, and it's changed in a vertical intercept. Well, what I'm curious about is those absolute value signs are kind of like parentheses. So if I add this parenthesis in here, what I've then got is perhaps a way of creating a horizontal shift. So I'm going to test that out, and I'm going to plot this function. And there I go. And this -3 can be thought of as a right-hand shift of 3. And so from this equation, I had the y-intercept to -4. Now I shift right 3 additional units. And this is another way of looking at the point-slope form. We still have the slope, and then this being an x point, and this being the opposite of the y point. You know, usually in point-slope form, you kind of have this -4 shifted over there. But in function form, we can't do that. So I can read this as a linear equation with a slope of 2 and going through the point 3, 4, the opposite of both of these values. Or I can read it as a modification to the parent function by adjusting the angle, doing a little bit of a rotation of it, and then a right and down shift of 3 and 4, respectively. So in summary here, for any function f of x, it seems that if I modify its parent function with the scale factor, it adjusts the angle that that graph makes with the axes. I'm going to call that an angle thing because in slope and with absolute value, I'm kind of mixing my terms quite what I want. If I modify it by adding a constant, it does that vertical shift to the graph. And if I add that constant so that it's in grouping symbols, parentheses with x, then what it does is it creates a horizontal shift to the graph that's opposite of the direction of that added constant. So f of x equals a times the absolute value of x minus h plus k would give me a squeezing or stretching by the factor a. It would give me a horizontal shift of h units and a vertical shift of k units. The vertex of this absolute value would be at the coordinates h comma k. And for the linear function g of x equals m times x minus h plus k, I used m here instead of a because we're used to m being slope. This would also be the same thing, a horizontal shift of h and a vertical shift of k. It would be the linear equation with slope m that goes through the coordinates h comma k. All right, I hope you've enjoyed watching this and that it has reminded you of a few different things, so we can learn a little bit more about quadratics moving forward.